tides on average. But the point is that they're quite reliable. So that's the sort of bulge that you see, particularly during lunar tides, greatly exaggerated as a result of these differential gravitational acceleration vectors changing as we move across the Earth. So we get these so-called lunar tides, and then we also get these solar tides. And I think there's a little movie here which may or may not work. So you can see that we have the daily tides, which are then modulated as we go through full new moon, which we call lunar and solar tides. And those occur every 2 weeks, which are superimposed on the daily and semi-diurnal tide heights as well. So the question is, can we make use, sorry, it's somewhere in here, can we actually make use of that change in gravitational energy? If you think about it, that gravitational energy change is pretty much inexhaustible as far as human beings are concerned. When we say inexhaustible, that's not quite correct. Does anybody know what happens to the energy, this gravitational potential energy change, over time, as a result of the bulge imposed on the Earth? Well, obviously energy is going to be lost through that process. 620 million years ago, the rotational period of the Earth was 21.9 hours. Today, it's 24 hours. Energy has gradually been lost through an increase in the rotational period of the Earth because it's losing rotational energy. But we're not too worried about that on those sorts of timescales here. As far as we're concerned, that potential energy source is inexhaustible. The question is it big, and can we make use of it? So, how do we extract energy from tidal changes? Well, there are 3 approaches. There's one called tidal barrages, which are very similar to dams. Effectively, as the tide height changes, water flows through a hole in some kind of dam that we might build, and that turns an electrical generator. And then, of course, when the tide goes down, the water can then flow back out in the other direction, and again we can get electricity generated. Or we could stop that flow of water back out and hold it for when we actually need it, and release it and produce power when demand requires it. There are also what are called tidal fences. So essentially those are vertical rotors which are placed off the coast. And then we have so-called tidal turbines. And those are effectively very similar to wind turbines, except they're underwater. Now, if you think about it, because of the density of water, it's about 800 times that of air. That should produce quite a lot of force on these turbines and produce a lot of energy. But remember, the currents are generally quite small. In fact, it turns out that tidal barrages, because of the area they can take up, are actually the most efficient way of extracting power. And we'll look at that in a minute. The other thing to remember is that these can really only be installed along coasts, and in particular in estuaries, and in particular certain types of estuaries with significant areas. So the advantage is, of course, we know an awful lot about tides, their periods, etc., and their location. So we should be able to produce a very good bottom-up estimate of the amount of power that we can extract from these tides. So it's a predictable energy source. So, a tidal barrage. Well, what is a barrage? Well, basically it's a dam, but essentially it's built right across an estuary, so it's just much bigger. And what you can see there is that at low water tide and high water tide we have essentially a change in potential energy as a result of the height of the water. And we're going to make use of that as the pool behind the dam or the barrage is filled. That's what we call the tide pool. So at low tide the water might be let out through the electricity generator to turn the water's potential energy into electricity. And the potential energy is simply G times H. Now be careful, H is not the difference in the tide change, which we call the tide range. We'll come to that in a moment. So, let's look at a typical European tide range. On average it might be about 4 meters. So that's the difference between low and high tide. And it's been estimated through various studies that the maximum power of one of these artificial tide pools or barrages, which is filled rapidly at high tide and then emptied as we want it to be at low tide through these various generators, so we can generate power in both directions if we want. But it turns out it's actually about 3 watts per meter squared. That number should sound a little bit familiar. It's roughly the same as our offshore wind power density for a wind farm. So let's think a little bit about the power density of these tidal pools. Remember, the semi-diurnal tide, water is changed every 6 hours, say. So the change in potential energy we're looking at here, every 6 hours, is simply the mass of the water times G times H. But H is the change in the height of the centre of mass of the water. That's half the range of the tide. In other words, H.2 in that previous diagram. So remember, the range is the difference in height between low and high tide. So be careful about H and H divided by 2. Read the question, if you ever come across a question about these barrages, very carefully. So, the mass per unit area covered by a tide pool is simply the density of the water times 2H, say. And remember, the density of water is roughly 1,000 kilograms per cubic meter. So, the power per unit area generated by a two-way tide pool is 2 rho H GH divided by the time over which we can access that energy, say 6 hours. Now if H is 2 meters in this specific question example, then the power per unit area of our tide pool is about 3.6 watts per meter squared. That's assuming we can extract all that energy. So I guess the question is, what's the efficiency of our electrical generator that we saw in the previous diagram? Well, actually these generators are very efficient. 90% efficient is not unheard of. So that gets us down to about 3 watts per meter squared, which is what we said before. Now, if we want to generate, say, 1 gigawatt of power, on average, over that diurnal cycle, we need a tide pool with an area of about 300 square kilometres. That's roughly a circular pool, 20 kilometres in diameter. And if you look around the UK, we can see various estuaries which have typical areas of around about 550 square kilometres, for example, the Severn Estuary, or the Wash in northeast England, off the coast of East Anglia, northern East Anglia. That's about 400 square kilometres. So those areas do exist. But let's start at the beginning. The actual first barrage built was actually built in France, and it was called La Rance. It was actually built in 1966, and it's been running for more than 5 decades. And the reason they built it there is because it has a pretty big tidal range of 10.9 meters, which is good. And it's been generating 2.7 watts per meter squared in terms of power density ever since. Still working today. Question is that a big number as far as global energy resources are concerned? Well, if we go back to our energy budget for the Earth, we've seen that the S infinity, the maximum we can get, is around about 0.1 Q per year from tidal power. So it's not really a big player on the global scale, but of course it could be important for relatively small communities or towns, etc., or locations that are suitable for installation of these tidal barrages. Also remember that tidal power is negligible over the open sea, and actually it's pretty insignificant along most coastlines, but as we said, it can be quite important, particularly if we have a very suitable estuary where the tidal flow velocity can be substantial and even amplified depending on the shape of the estuary. For example, the La Rance tidal barrier can generate about 240 megawatts, and that's actually relatively small but it actually was one of the biggest for several decades, since the 1960s. Now, if we do a survey, it turns out that the best cases in the United Kingdom for tidal power are the Bay of Fundy, Bristol Channel, Severn Estuary. And that's not just because it's a very big estuary, it's because the shape of the coast leads to funneling of all those strong incoming tides into narrower and narrower regions, and that tends to create a resonance close to the tidal frequency. And it actually can lead to some very high tidal amplitudes, up to 40 metres in the Bay of Fundy. A bit less in the Severn Bore, 10 to 11 metres, say. So that makes it possible to utilise that rising and falling tidal water by, as we said, forcing it through these electric turbines. And indeed, if we look at the Bristol Channel region, a design study estimated that depending upon where you built the barrage, you could get power output of the order of 1,400 megawatts to 15,000 megawatts. In fact, this is from the report which looked at the various locations you can build such barrages. So you can see we start out here, the so-called outer barrage, we can get 15 gigawatts. We build a barrage here, we can get 8 gigawatts. If we go up here, we can get 1 gigawatt. Now, as the tides are essentially funneled into a narrow estuary, of course the flow increases, but of course the area decreases, although the height can also increase. So there are pros and cons to where you build things, but typically you would go for high velocity, high tide, with a large area behind the barrage, as you can see in the outer barrage there. However, there aren't very many places around the world like that. Surveys show that there are maybe 20 to 30 of these sorts of estuaries worldwide. So if you sum up all the potential power we can get from those estuaries, we're looking at a global figure of about 20 gigawatts. That's only 10 to the minus 4 cube per year. Not only that, building these big barrages come with a lot of environmental problems. Particularly in the UK, proposers of such schemes have failed to convince governments and the public that they've actually addressed those problems readily. So this is a sort of a snapshot history of the statistics for tidal power since the 1960s. As we said, the first one built was Lorance in France, with its 8-metre tidal range, 240 megawatts capacity. The area of the tide pool behind it was about 17 square kilometres, so it's pretty big. Subsequently, lots of other peoples followed suit, but you can see that the tidal pool area was actually pretty small, so the amount produced in terms of megawatts was actually also relatively small, even though the tidal range in some cases was close to Lorance. So Lorance actually remained the biggest barrage in the world until 2011, when Siwa Lake in South Korea was built. And they have 30 square kilometres and were able to produce 2,540 megawatts. So that then became the biggest. And since then there have also been lots of other proposals. These just show some of them which have been proposed. Some of them are huge and potentially can produce up to 15,000 megawatts, similar to the Severn Estuary in the UK. But if we focus just on the UK, the number of schemes that were proposed were there were 8 of those big large ones, but there are also about 34 very small ones, because the UK is basically an island. We've got lots of these little estuaries. And if we sum up all the various generating capabilities, we're looking at a potential electricity supply of around about 50 terawatt hours per year. And that potentially could contribute about 17% of the UK's electricity needs, if they were all built. Oh, sorry, that's just a picture of the barrage in Siwa Lake in South Korea. So you can see essentially it's basically a barrier across the estuary, with lots of turbines built below. Okay, what's next on the list? Well, we have geothermal energy. Now, we estimated the total heat flowing out from the centre of the Earth to the surface was around about 1 cube per year. But if we were to average that over the entire surface of the Earth, that comes out to only 60 milliwatts per meter squared. So that's extremely small and not really viable as a global energy source. But again, it might be useful for local communities. And there are actually two possible ways of extracting such energy. We can look for hotspots. In other words, the heat flow coming out of a very narrow region might be extremely large, and that's usually associated with volcanic areas. And in fact, we've actually utilized such hotspots, or at least they have been utilized for over 100 years in certain regions. So, as we said, some of those have already been exploited. The world's first geothermal power station was actually at Larderello in Italy, built in 1904. And it now yields 400 megawatts of electrical power. If we look globally, the total installed capacity is around about 4 gigawatts, mainly in California, Iceland and New Zealand. But that's about 10 to the minus 4 Q per year. Surveys suggest that maybe we could increase that by a factor of 10 to about 10 to the minus 3 Q per year. Another approach is the so-called hot dry rock approach. You might have heard about this, or at least a related process. What you do is you take water and you pump it down a borehole that's been drilled several kilometers into the rock strata, and then you basically suck that water back up another borehole parallel to it. And of course the temperature change as a result of going down several kilometers should heat the water up to about 200 to 300 degrees centigrade, and by the time it gets up it's supercooled water and steam, and you can use that to drive an electrical turbine. Unfortunately, the experiments that were conducted did not produce very good results. Turned out the rock strata they were drilling in was very porous, so the water temperature by the time it got back to the surface fell much quicker, much more greatly than expected, and it didn't really work terribly well. Put too much energy in to actually get any useful energy out. So there are no current experiments planned, and there's no projected resource estimate for that particular energy resource, unfortunately. However, there are some countries, as we said, that do make use of it. Here, for example, is the Reykjavik power station in Iceland. And Iceland actually makes a lot of use of these hotspots. They actually have 5 geothermal energy plants. And that actually generates just over a quarter of their electricity needs, provides heating and hot water to 87% of all the buildings in Iceland. The remaining energy they get from hydropower, less than 0.1% from fossil fuels. So they're doing pretty well. It's also a nice tourist attraction. However, there are some drawbacks because they're next to, those hotspots are next to volcanic fissures. You also get emissions of hydrogen sulfide, which can affect and has affected the health of local populations, so it's not perfect. Okay, so let's come to the big player in renewable energy sources, solar. It is the largest environmental source. Remember we said the net input from the sun was about 3,000 Q per year, so obviously that's got a very large potential if we can make use of it. Let's try and make a usable top-down estimate for solar power. Let's start out by saying the area of the world is simply A. Let's assume we can only build solar panels on land. So that gives us about 0.3A usable area. Of course, we have to use land for other things, particularly for growing food, etc. Also, 50% of the world's land areas, it turns out, are useless for either solar power or food production. So let's be really conservative and say 5% of the remaining area could be given over to solar power generation. So the usable area is now come all the way down to about 0.0075A. Now, if the maximum efficiency of conversion of solar to electrical power is 20%, 0.2, that's a bit of an underestimate because there are now more efficient solar panels that can go up to about 0.3, but let's assume 0.2. The total amount of incoming solar energy that is usable is then 0.0015 times 3,000, 4.5 Q per year. That's pretty good. So if the radius of the Earth, as we said, was 6,360 kilometers and the power density comes out to be about 19 megawatts per square kilometre. Not bad. That's assuming that only 50% of the collected energy is effectively used. That's actually a lot less than all the other environmental energy sources we've been talking about, and that's actually been nearly achieved in demonstration solar farms in California. It was achieved first of all in 2011 by this 7 megawatt power station that was built there to demonstrate how reliable they could be. So if we move forward a little bit to 2013, California, Nevada 1, as it was called, Copper Mountain 1. Various solar plants built then had a capacity of about 350 plus megawatts. Those are the largest solar power installations in the world until 2014, when they built another one at a location called the Ivanpah facility, which went up to 370 megawatts, and they've got bigger and bigger since. And that essentially is the Ivanpah facility there. So you can see the advantage of the United States is they've got a lot of area with very little in the way of cloud cover, etc., to interfere with their solar power collection. Okay, let's do a bottom-up estimate. Well, it wasn't possible to do that in 2012 because then solar power systems were far too expensive to be built into very large arrays, but since then the costs have come down very, very quickly. So a lot of the engineering estimates are still in the process of being developed, but the potential power depends on a lot of factors, including weather, climate, seasons. And a lot of those are not accounted for in our previous top-down estimate. So it's got to be an unrealistic upper estimate. So at the moment what we need to do is look at, say, maybe half a Q per year as being attainable, realistically. So in 2000, the installed capacity was 700 megawatts. Half of that was in California. But new technologies has been tried elsewhere, including Australia, China, using new approaches, and that's actually increasing the potential yield significantly. So we're still waiting for the latest survey as to how good those are. But it must be stressed that once we depend on a resource, such as solar power, for a substantial fraction of energy, then we have to think about some form of storage because the sun doesn't shine at night. So, if we wanted to do a global calculation of the available energy in kilowatt hours, that's the equation at the top there. So we need the area of our total solar panel farm in meters squared. We need the solar panel yield in percent. We need to think about the annual average irradiation on our tilted panels, which assume are pointing perpendicular to the sun. We also have to think about how much shading there might be at a particular location. And we also need to think about the performance ratio. In other words, what are the losses? And they can be quite significant. They can range between 0.9 and 0.5. Most people assume a value of about 0.75. So there are all these various losses to think about. Inverter losses. These solar panels tend to not be as efficient when the temperature goes up because they don't work quite as well. That can range from 5 to 20%. Then there are cable losses, the shadings we mentioned, losses at very weak radiation intensities. We have to keep them clean. If you cover them with dust or even snow, then of course that's going to reduce the losses depending upon how often you clean them. And there are also various other losses we haven't even considered here. But based on that, you can produce a map that looks a little bit like this. So you can see that the best places are the equatorial and southern latitudes, where we can get anything over 1,500 to 2,500 kilowatt hours per meter squared. Obviously somewhat less, say 1,000 or so when we start going into the upper mid latitudes in the northern hemisphere. Some of you might like to look at this region and ask yourselves, why is that so low? I'll leave you to think about that. Okay, this is an interesting one. This is a different way of extracting solar energy. what we've been talking about previously are what are called PV solar farms, or photovoltaic solar farms. So we're using these photovoltaic solar panels. But there is another way you can extract energy from the sun, that's called solar thermal energy. And essentially what you do is you have a whole bunch of tracking mirrors, which may cover several square kilometers. They're sometimes called heliostats. And they focus and concentrate the sun's light onto a so-called power tower. And that so-called power tower, or receiver, onto which all the solar energy is focused, contains a molten salt. And that's heated by that solar energy up to about 500 or so degrees centigrade. That molten salt then flows into a thermal storage tank where it's stored, maintaining 98% thermal efficiency, and then it's eventually pumped through a steam generator. And that steam drives a standard turbine electrical generator. That's known as a Rankine cycle. I'm sure our physicist friends know about that. And it's similar to a very standard coal-fired power plant, except it's fueled by this clean and free solar energy. Now, the advantage of this design is it can operate at higher temperature, obviously. Thermal energy at higher temperatures can be converted to electricity much more efficiently, and you can actually store it a little bit longer for use later, even after the sun's gone down. And again, one of the largest was built at Ivanpah in the Mojave Desert, California, and was able to generate about 377 megawatts. So that's what they look like. So this is in Mojave Desert. You can see the central tower there, and these are essentially metallic mirrors focusing all the radiation onto those towers. So the fluid is stored at the top of those towers there. Why build those instead of solar panels? Well, it was initially thought it would be a bit cheaper. However, there have been lots of arguments in the press recently and in industry suggesting that they're not as efficient as people think they are. So again, the jury's out with respect to how much they might contribute to solar power conversion in future. Okay, let's move on to biomass or biofuel, which was also on our list. We can, for example, grow crops. So we're basically utilizing a process of photosynthesis to convert solar energy to a fuel mass. And again, our top-down estimate from our previous figure for photosynthesis was 1.3 cube a year for the entire biosphere of the planet. However, of course, we have to use 40% of that for food. And as food's the priority, we should not really expect to use more than maybe 10% of the total productivity from photosynthesis for fuel use. So we're looking at around about 0.13 cube per year. So not insignificant. Remember, the year-round solar flux is 150 watts per meter squared at the surface, or 150 megawatts per square kilometre. Fast-growing plants convert that energy into, or rather they fix it, and convert about 1% of it into plant mass. If we were to convert that fuel, let's say with an efficiency of 25%, then we get an output of 0.4 watts per meter squared. It's not great, but it's sort of almost free, though we have to take into account extracting that fuel from the plant material. Now in Brazil, energy from sugarcane has been retrieved at those kinds of rates, and you can actually get somewhat better results depending on what type of crop or plant you produce. For example, it's claimed you can get much better outputs if you use, for example, cassava roots, which is a widespread tropical fruit. If, suppose we were to extrapolate that number to the United States, and let's suppose 10% of land is available for biomass fuel production, you could get maybe 10 to the 19 joules per year, or 0.01 cube per year. Extrapolate that to the globe, you're looking at 0.17 cube per year, roughly in agreement with our previous estimate. So again, not a huge number. What about other sources? Well, let's look at alternative sources in the UK and see what we've got available. Let's do a budget. Wind, we talked about a lot. We're looking at 230 terawatt hours per year. That's what we call our S2 value. Waves, maybe, if we were to build those wave generators, which we're not now because the company went bust, 60 terawatt hours per year. Tidal, of which the 7 bore, if it ever gets built, would give 13 out of a total of 45 terawatt hours per year. Hydropower sites that are not yet developed, 2 terawatt hours per year. And recycling and burning of waste material, that's treatment to yield oil gas for direct incineration, 150. So we're looking at a total of 487 terawatt hours per year. For comparison, if we look at a continuously running 1 gigawatt power station, gas or coal, it typically delivers around about 9 terawatt hours per year. And the total power generated in the UK in 1975, for example, was 210 terawatt hours per year. So we're well placed for several of those sources, but not so much for solar power or indeed hydropower. So again, we're not really looking at more than 25 to maybe 40% of our total power from similar alternative sources. Okay, let's continue. So the potential yield from environmental sources does exceed electrical power generation in 1975 by about a factor of 2. If we were to exploit all of those, we would manage to replace all fossil fuel used in electricity generation, 900 terawatt hours per year. We could provide an additional 277 terawatt hours per year to be converted to electrical power. If that additional energy was then used to replace fossil fuel-based heating at 75% efficiency, then we could reduce our fossil fuel burden by a further 370 terawatt hours per year. So all these calculations can be made using these basic assumptions. So we could potentially reduce the fossil fuel demand by maybe 1,270 terawatt hours per year. So if we were to use 2,500 terawatt hours per year, then we would obviously replace the total burden, or rather we'd reduce the total burden to 1,230 terawatt hours per year. Why? Remember, there's an efficiency associated with burning fossil fuels to produce electricity. That efficiency is typically only about 30%. So that would be very significant in terms of the required reduction in our contribution to our total CO2 emissions. However, it's not sufficient to replace coal and gas because the residual figure is actually larger than the 1975 contribution from coal. Coal contribution to energy reduction is, however, a lot less now than it used to be. It's fallen to actually less than 300 terawatt hours per year. So this is basically a summary of the alternative resources that we have discussed. So the far left, we're looking at the power units in cube per year from all of those sources: hydro, wind, waves, tides, geothermal, solar, and biomass. We have some power densities that we've estimated, but sometimes they're not always available. We're assuming they're going to be extremely small. S1 is what we call the present installed capacity. S2 is the estimated maximum potential capacity. And S infinity was from our previous figure, which showed the natural energy flow in the Earth climate system. So you can see that hydropower is actually currently very small, 0.01, maximum about 0.1 out of a potential maximum of 1.3. Wind, on average, is small, estimated potential 0.2 out of a maximum of 12 from our energy budget, top down. Waves, well, effectively I think we can ignore those. Very, very small installed capacity. Maximum potential is negligible. Tides, again, globally are small, so we're looking at maybe 10 to the minus 3 is the maximum potential out of 0.1 for our budget. Geothermal, again, very small, 10 to the minus 4 to 10 to the minus 3 maybe, between the present and the estimated maximum potential. Again, out of a maximum energy flow of about 1. Solar is small, but the estimated maximum potential could be as high as 4.5. This maximum energy flow is based on just land-based extraction of solar power, as you can see there. Biomass is actually relatively significant. We're talking about 0.15 as an estimated maximum potential out of 1.3. So we're looking at a total maximum of around about 5 cube per year, compared to a present installed capacity, well, that's gone up a little bit since then, of about 0.01. So those are the sorts of numbers we have to think about. So obviously we've got a lot of work to do globally to get up to our maximum potential of around about 5. Okay, we'll skip through this. This just shows, yes. Well, okay. We mentioned that if you start to look at solar in anger, we're going to have to think seriously about storage in order to match demand with the available energy. So this is how effectively our thinking has to change. So in the past we simply had power generation, plants, consumers, houses, factories, but now we have to think very carefully about storing that energy in order to provide supply when demand is needed, because of the intermittency of our renewable resource, mainly wind and solar. And that's why new factories like this one, Tesla Gigafactory as it's called, being built in Nevada, you can see it uses multiple renewable energy sources. You can see all these solar panels providing a majority of the power, but notice up to the top right we've got a wind power farm also providing power, and that's being fed into very large battery storage facilities to make sure that that power is maintained and available on demand. This is actually a 35 gigawatt hour production facility supporting production of electric vehicle production. We'll come to all electric economies next week. And of course you may have heard in the news that Tesla have also provided a 100 megawatt grid of batteries to provide extra capacity for demand in Australia. And that's it there. So effectively that is now providing backup to wind power farms to make sure that there are no intermittent dropouts in power for that part of Australia. So it is possible. So I think we've got through most of the energy flows, the alternative resources that are available. And what you can see is that, well, we'll summarize this again next week, but what you can see is that we've got a lot of work to do to extract usable energy to the levels that are going to be required based on our estimate of 3 to 5 Q for the end of the century. So we'll make a brief start, and we're going to talk about definitions of resource and reserve, because we need to think about the timescales involved with respect to, well, how long have we got to sort out those renewable energy replacements based on our current consumption rates, and in particular how long have we got before our non-renewable energy sources run out. Okay, so up to now we've kind of made some projections about the amount of energy we can use before excessive global heating prohibits increases in consumption. Currently that's been argued about. 1.5 degrees C is the current maximum we're looking at, but it could be as high as 2 or 3, depending upon which scenario you look at. We then made some projections about the amount of energy we're likely to use when the world population stabilizes by the end of the century, 3 to 5 Q per year. We saw that that was a large increase in energy use globally, and we questioned whether or not we have the resources to actually fulfill those requirements based on current energy resources. Now, to answer that question, we have to think very carefully about A, the amount of energy available at the moment, and how long some of those components of that energy resources can last. Now, normally energy is split into 3 equally sized sectors. household and commercial, industrial, and transport. Now, the main energy source, at least a few years ago, remained overwhelmingly the burning of fossil fuel. Nuclear and hydroelectric contributed actually only relatively small amounts. But over the last 5 to 10 years, there's been a rapid increase in renewables, as we saw previously. The other thing we have to remember is that that energy is distributed largely based on what we call fuel burnt at the point of use. Only about 10% is actually distributed as electrical power, although that, in effect, represents 34% of the total budget because of the relative inefficiency, I should say, of converting fossil fuel to electrical power. Typical power generating station burning gas or coal at its maximum efficiency can only do about 30 to 34% conversion of the available energy in the coal mass or oil mass into electrical power. So, how have things changed in terms of the overall energy from production of fuels? Well, this is a bit of an old, sorry, you probably can't see it very well, you need to look at it online. This shows the million tons of oil equivalent used for petroleum, natural gas, coal and primary electricity from 1970 to 2000. Primary electricity is what we call generated from nuclear. So what you can see is there's been a big shift in the various components from 1970 to 2000. Not only is the total in terms of million tons of oil equivalent gone up significantly as the global population has expanded, you can also see that the relative contributions have also changed subtly. So if we look at the inland energy consumption between 1970 to 2000, you can see a big change in terms of the coal generated between 1970 and 2000. Coal's gone down significantly, and the renewables and waste have started to increase, as you can see from that top bar, and that increase is continuing today. The question is, can that increase be maintained, and are we ever going to be able to replace gas, coal and oil completely? Well, let's think about that. Okay, this is another pie chart which shows the difference between 1990 now and 2000. And so if we look at the natural gas, oil, coal, imports, and you can see that little purple one, that's actually hydro and other fuels, renewables. And you can see that that hasn't actually changed, didn't change an awful lot up to 2000, but it is now changing significantly. Coal has reduced significantly, but it was replaced mainly by natural gas. So that's what we have to aim for in terms of replacing future energy use. And again, this data is from 1980 to 2000, and you can see the terawatt hours produced has also increased significantly as we discussed previously. But the question is, we're looking at maybe about half of that energy production source needs to be replaced by renewables if we want to reduce our CO2 emission footprint. We also said that we have to think about the time scales. Now, let's think a little bit about oil resources, because that's a good example about how to calculate how long our fossil fuels are going to last. Now, historically, oil companies have mounted this continuous effort of exploration to maintain oil reserves, because they've got to sell it. And that reserve is typically equivalent to 10 and 20 years of current production. That generally means that the production tends to lag behind, maximum production, tends to lead the maximum production, tends to lag behind the discovery. It also means that the reserves of that oil has increased as production has grown. We tend to discover more and more. However, as we'll see, what we discover tends to be smaller and smaller oil fields, because we tend to discover the big fields first. what we have to do is measure what we call the resource limit for oil. So we're going to look at an analysis by two scientists, Campbell and Lehrer, which was published in Scientific America way back in 1998, but the methodology is still used today. And they said we have to think about three numbers in order to be able to project future oil production and how long it's going to last. First of all, we need to know the number that tells us the total of how much oil has been extracted to date. Okay. Second number, we have to have an estimate of the reserves. In other words, the amount of oil that the companies are able to pump out of their existing discovered oil fields. And then the final number, which is a bit more vague, is a guess at the quantity of what's called conventional oil remaining to be discovered and exploited. So the question is, how do we get those three numbers, and what kind of equation have we got to put them into in order to estimate when our oil is going to run out? Now, together, they all should add up to what we call the finite quantity of the resource, which we're going to call little r lim. So that's the finite resource for oil. And we also have to think about the cumulative production, which we can estimate quite well, because remember, oil companies always monitor the amount of oil flowing out of their oil fields from their wells. However, that record is not perfectly kept, but it's good enough to make reasonable estimates of what the cumulative production actually is. What about the final one? It's very hard to find estimates of the total current reserves. There are lots of reasons for that. Mainly because those figures which are provided to trade journals from oil companies and governments, those figures have a lot of problems associated with them. First of all, estimating the size of an oil field is not an exact science. Normally what happens is that a scientist, a geologist, will provide a range of reserve estimates and associated probabilities about the sizes, and they're produced in a private report to the producer. Now, in practice, companies are often vague about the confidence of their reserve or the estimates, and they may publicise whichever figure suits them because they want to enhance their market value and get orders. Now, in the case of OPEC countries, the larger the reserve, the greater the amount they can export. So there is a temptation to be rather optimistic about your estimate for reserve. Now, a good example of that was a sudden and suspicious leap in reserves by 6 of the 11 OPEC countries in the late 1980s. That happened after various governments took over the fields from private companies. In part, those estimates were warranted due to subsequent better updates in surveys of previous rather conservative estimates and extrapolations. But there were no new fields discovered in that period. There were no major technological breakthroughs in terms of improving the efficiency of extracting the oil, and yet the estimates suddenly increased by between 42 and 197%. So there are some difficulties with using those numbers. So next week we'll continue by looking at how we're going to use some of these estimates to estimate the lifetime of fossil fuels, and we'll talk about something called the Verhulst equation. Okay, thanks for coming.
You available next Monday or Tuesday?
Monday, probably. Just check.
I just last week I finished the monthly experiment.
All right, yeah.
And today I just get the monthly first data.
Good.
I will produce some for us.
Good. Ian might be busy, but come see me first. You've been doing field work, but come see me first. Let me just check.
Back in here, she said
Busy. Okay, I'm not available from 11 to 12. I have to have a Skype with Dr. Ellen. But I'm available before 11. That's okay. And then hopefully in the afternoon.
Afternoon. Available 11.
I am available in the afternoon. The Skype will only last an hour. Thank you.